Hello, my name is Tom Stephen.
Hello, I'm Dave Satterley.
Hi, I'm Ishita.
Hi, I'm Mahima.
Our project is called MCube at UnionLabs. The high-level goal of this project is really twofold. First, make progress towards getting the MCube testbed understood, configured, and operable in the Wings lab. And second, make the testbed operational remotely by integrating it with AWS. We have made progress on both these fronts, as will be described.
MCube is an open source millimeter wave software radio platform that was developed by UC San Diego. Our objective is to set up an operational testbed, allow remote access and configuration while integrating it with Union Labs. To set up an operational testbed, a series of codebooks and scripts are run. After the initial setup, we are then able to establish communication between the transmitter and receiver routers.
We will quickly demonstrate how to initialize the routers to perform benchmark communications. We start with switching on the PDUs in the following manner. Once the routers are powered on, there is a 1 minute wait before we can ping them. Green LED is an indicator of the initial setup completion. After successful ping from both routers, we can proceed to load codebooks and assign TX mode and RX mode to the designated routers. After successful ping and loading of codebooks, we can now turn on the bridgeboard connections using the PDU. Once the bridgeboards are connected and the TX-RX modes have been assigned, our initial setup is complete and communication can be started.
The M cubes have the following blocks. I'll briefly explain the communication of the M cube. The bandpass units, our USRPs generate a signal that is sent to the routers via bridge board, controlled using FPGA. The routers ramp up the frequency to millimeter wave range of 60 GHz before transmitting. Our phased array, 8 RF chains, and 256 antenna elements control the beam of radio waves useful in radar application.
Now that the initial setup is complete, we can demonstrate the communication using benchmark code. We are currently communicating at frequency of 3.01 GHz, rate 50,000, modulation scheme BPSK, and gain 90 dB to get efficient response and higher correct packets. We can see that by changing modulation scheme to QAM, there is a significant reduction in efficiency with zero correct bits transmitted, even with a very high gain. There is a timer error that was observed at higher rate of 100,000. Hence, we can observe that for arguments stated previously, even with a change in orientation, the communication is reliable.
This next portion of the project aims to enable remote access of the MCube millimeter wave platform for the ultimate purpose of integration into a federated testbed platform called UnionLabs. To accomplish this, we must provide both remote configuration support for the MCube routers as well as remote control of the experimentation platform. Amazon Web Services is a cloud-based platform offering numerous facilities, including Cognito for authentication, IoT Core for device management, and MQTT for configuration and device state synchronization. These services are key to realizing our objective.
In order to access the remote testbed interface, the user must log in to an authorized UnionLabs account. Accounts and login facilities are maintained through the Amazon Cognito service. This login page is hosted via Cognito. When the user logs in, they are redirected to the testbed web page. Included in the redirect request is a token that can be utilized by the web application to authorize future requests to the required AWS services. In conjunction with Cognito, alternative OAuth platforms such as Google and Facebook can be used to provide authentication services.
The web-based testbed interface is implemented using HTML and JavaScript. It is hosted on Amazon's S3 storage platform. After an authorized user loads the page, it will begin subscribing to various MQTT topics related to the MCube devices. The web page must utilize the authentication token to access the MQTT service. After the MQTT service is connected, the web page will utilize the device shadow to update its local representation of the device state. The right side of the screen displays this device state information, as well as an interface to send configuration and control commands to the platform. On the left side of the screen is the remote control interface, a graphical interface to the experimentation platform connected to the MCube routers. The Xpera software is used to power the real-time remote access. The data channel is established through a reverse proxy located on an Amazon EC2 instance.
At this point, the power on command is sent to the testbed. This command updates the device shadow state, which is sent to and operated on by the experimentation platform. This command will turn on the power port and begin the booting process for the MCube routers. When booting is completed, the user interface will update to reflect the ready status of the routers. At this point, the user can load in their experimental phased array code books and enable the transmit and receive modes for their respective devices, at which time the user can enable power to the bridge boards, which inject generated signals into the RF chain. Once the bridge boards are powered up, the platform is ready for experimentation.
As previously mentioned, MQTT is utilized as a communication channel between the experimentation platform and the user web interface. Control is done via both device shadows as well as a command and response protocol. In this section, we will utilize the AWS IoT Core test interface to observe some examples of the MQTT messages flowing between the web interface and the experimentation platform. Power state is controlled through device shadow updates, which trigger events on the delta topic. This topic indicates a delta between the current and desired device states, which must be resolved by the experimentation platform. Upon resolution, the platform posts its own update to the device shadow, which is reflected in the web interface. The command and control is done using a request response protocol. The web interface publishes MQTT messages containing a command payload to the request topic. When the experimentation platform receives a request and performs the desired action, it will publish the status to the response topic, indicating completion.
Moving back to the web interface, we can now perform our desired experiments. For this demonstration, we will be utilizing the USRP's UHD FFT utility to realize a millimeter wave spectrum analyzer. Notice that the center frequency is at 3 GHz with a bandwidth of 6 MHz. This access can be deceiving as the MCubes are actually operating in a 60 GHz millimeter wave band. In fact, the RF chain has two separate mixing stages before reaching the USRP's analog front end. It is first mixed from 60 GHz to a 15 GHz intermediate frequency, or IF, inside of the MCube. This signal is routed through the bridge boards, where it is again mixed down to the baseband signal that is received by the USRP. This results in the frequency range being represented within the operating range of the USRP. The USRP connected to a second MCube is configured to transmit a BPSK signal at 3.001 GHz. When the transmission begins, we can see the signal appear on our spectrum analyzer. After the experimentation is complete, the user interface is used to power down the bridge boards and MCube devices.
In conclusion, the result of our project was that we calibrated the testbed and achieved a successful initial setup. We enabled remote testbed access, including user authentication and customized testbed-specific controls. We proved out the possibility of integration into a federated system built upon a standard platform, in this case AWS. And we enabled communication between the MCube platforms.
Further, we plan to continue refinement of our user interface, continue usability testing, support and verify a wider range of test scenarios, including RF communications, radar, and other millimeter wave research, integrate with larger UB UnionLabs project, and we also plan to add support for storing, modifying, and sharing of configurations, datasets, and test results.